Welcome to 37th lecture on numerical analysis. We are studying numerical solution of ODEs, ordinary differential equations. In last lecture we studied the Taylor series method for the numerical solution of an ODE, but in this lecture we'll study Runge Kutta method. It is pronounced as Runge Kutta. Runge was a scientist, Kutta was also a scientist, so it is actually a method proposed by two scientists. Right, so the method is very simple. Given an ODE, dy by dx is f of xy and an initial condition that y of x naught is y naught, we move step by step. We are also given a step h. H is the step size, so we are given h, the step size. So we take smaller steps unless we reach to the desired value of x. So we keep on taking small steps unless we reach to the desired value. So this h is the step and can be the starting point, where this x naught is a starting point. For example, x naught is a starting point. We take one step. This is x naught plus h, x naught plus h. This is x naught. The starting point is x naught. We start from x naught, we take a step and move to another point we call x naught plus h, and then we take another step and move to another point, that is x naught plus 2h, and then we take another step and we go on and on and on. So we work like this. So we keep on taking steps starting from some initial value x naught, and we move to x naught plus h, x naught plus 2h, x naught plus 3h, and so on. And it is a small step size, but the formula that computes y at some desired value n plus h is based on the value of y at some n, some previous value of y, n, or the y of at the value of y for some previous value of x, in fact, is based on k1, k2, k3 and k4. But k1, k2, k3 and k4 are computed using these formulas. K1 is f of x and y n, and n is actually our point for this particular iteration. N, it may be x naught initially, then it is x naught plus h, then x naught plus 2h, etc. And k2 is computed as f of xn plus h by 2, and yn plus h by 2 k1, where k1 is this k1. And the formula for k3 is dependent on xn, yn, h, and the k2 that we computed in the last step. And the formula for k3 is dependent on k3, and the formula for k4 is dependent on the value of k3 that we computed in the last step. So these formulas are actually interconnected. K2 is dependent on k1, k3 is dependent on k2, and k4 is dependent on k3. Right, so based on these simple formulas, we take steps and we compute y at each step unless we reach to the desired value of x, where we are supposed to evaluate y. Right, so let's solve an example where f of xy is dy by dx is given to be equal to y, and this initial condition. This is the initial condition, y of 0 is of 1. This is the initial condition, and there is a small step size h is also given to be equal to 0.25, and we are asked to compute y 0.75 given y 0 is 1. So we start from 0, we take steps 0.25. The first step takes us to a value equal to 0.25. The next step takes us to 0.5, and then the next takes us to 0.75. So we require 3 steps. In this case, we'll start from 0. So the initial value is 0, in this case 0, and the first step will take us to 0.25 because we take the first step equal to 0.25. the next step takes us to 0.5, and finally we will be at 0.75. So we'll start from 0 in this case, and we'll take 1, 2, 3 jumps. So let's take the first jump with n is equal to 0. So we are at n is equal to 0 at this point, and we are able to take the first jump to compute the value of y at 0.25. So y of 0.25 is y naught, n is 0 here, n is 0 here. So y of 0.25 is y naught plus h by 6 in the same formula, this formula, and we put this in this formula. K1 comes out to be f of x naught, y naught. F of 0,1 is 1 because f of 0,1 is 1 because f of xy is y here. So whatever is the value of y, f of xy is the same. F of 0,1 is a 1. So we compute k2, k3 and k4, and finally we plug all these in this equation. Y of 0.25 is 1 plus, where 1 is y of 0. Y of 0.25 comes out to be 1.28. And we keep on moving. Now we are going to take the second step to take us to y of 0.5. For that, the initial values is 0.25 and y of 0.25 is 1.28 we have just calculated. And then k1 is f of x.25, y.25, and x.25 is 0.25, but y.25 is 1.28, this one. And f of 0.25, 1.25 is 1.28. And we keep on moving. We calculate k2, k3 and k4, and then y of 0.5 by plugging all these in the basic formula for Runge Kutta method, and y of 0.5 comes out to be 1.64. And similarly, for y of 0.75, the initial point is the initial value is about 0.5 is 1.64. This one we have just calculated. X of 0.5 is 0.5, and the step size is the same, and we use the same formulas for k1, k2, k3 and k4, and we plug those in the basic formula, and y of 0.75 comes out to be 2.11. Right, the exact solution for this ODE is log of y is x plus k, and we compute e anti-log on both sides. E to the log of y is y, and then we put the initial condition, and it comes out to be a very important result. Y of x is e to the x based on these initial conditions and the given differential equation. So the exact solution for the exact value of 0.75 at which x equal to 0.75 is 2.1. So if we plug 0.75 here, the exact value is 2.1. But what's the approximate value based on Runge Kutta method? It's also 2.1. It's 2.11. So they are really close, they are approximately equal. The percentage error is almost 0%. So based on based on this analysis, the Runge Kutta method, or the analysis presented in this example, I have written a Python code for you, and you will be required to play with that code. You will try different values of h, you will try different values of x, the desired value of x, you can try different value of h, and you see that you reach to a value that is very close to an approximate value that is very close to the exact value, proving that Runge Kutta's numerical method is a very useful and very close to the exact method. or very close, it brings an answer that is very close to the exact answer. Right, that's all for this lecture. In the next lecture we will continue with at least one more example and we'll be solving that using Runge Kutta's method. Thank you.